Back in 2014, this new AI model called GoogLeNet came along. And it didn't just get a little better at seeing images, it completely changed the rules of the game. It introduced a new way of thinking about efficiency and scale that honestly is still shaping AI today. So let's break down what made it so incredibly special.
So here's the problem everyone was wrestling with back then. How do you get a network to recognize features at all different scales? I mean, think about it, right? To really understand an image, you've got to see the tiny, fine texture of a piece of fabric, the medium-sized shape of a button, and the overall silhouette of a coat, all at the same time.
Well, the obvious solutions had some pretty serious drawbacks. You could try going deeper by just stacking more and more layers, but that was computationally brutal and an absolute nightmare to train. Or you could go wider, cramming more features into each layer, which also just ate up processing power. So you were kind of stuck. It felt like this classic trade-off with no easy answer.
And then along comes GoogLeNet with this absolutely brilliant solution, the Inception Module. Instead of forcing a choice between deep or wide, it found a way to do both, but efficiently. The core idea was to process the image at multiple scales in parallel, and then, here's the kicker, it lets the network itself figure out which scale is the most important for whatever it's looking at.
Okay, so how does this thing actually work? Well, you can think of it like a team of specialists, all looking at the same image. The first branch, it uses a tiny 1x1 filter, kind of like a magnifying glass for superfine details. The next two use 3x3 and 5x5 filters. That's like your standard view and your wide-angle lens. And that last branch, it uses pooling to get a complete bird's-eye view of the whole scene. And they all do their job at the exact same time on the same input.
Right, so here's the really crucial part. Each branch specializes. You've got 1x1s for simple features, 3x3s and 5x5s for bigger and bigger patterns, and max pooling for that general overview. But the secret sauce, the thing that makes it all work, is those little 1x1 convolutions they put before the bigger filters. They act as a bottleneck, shrinking the data down and making those wider, more expensive operations totally affordable. It's just genius, honestly.
And when you look at the code, you can see this concept laid out perfectly. You've got these 4 distinct branches, branch 1 through branch 4, each one processing the data in its own way to capture different kinds of features. Then, at the very end, all those unique insights get stacked together, or concatenated technically, into a single super rich output that gets passed on. It's just a really elegant way to combine all these different perspectives.
All right, so that's the theory, which is super cool, but let's get real for a second. How does this beast of an architecture actually work in the real world? We're going to see how this powerful idea gets adapted for a much more common task, classifying simple images of clothing from the Fashion-MNIST dataset.
I mean, you wouldn't use a sledgehammer to crack a nut, right? The original GoogLeNet was built for these massive 224 by 224 color images. For the tiny 28 by 28 grayscale images in Fashion-MNIST, that's just complete overkill. So what you do is you intelligently scale it down. We're going to use fewer Inception modules and just reduce the number of filters inside them.
So let's follow the data on its little journey through our network. It starts out as a simple 28 by 28 image. Now, as it flows through the layers, you can see the image size gets smaller and smaller, but look at what happens to the number of output channels. That's the number of features it's learning. That number just explodes. The Inception modules do all the heavy lifting, and by the end, it's all condensed down to just 10 possible outputs, one for each type of clothing.
And here's what it looks like when you put it all together. You can see how it's built piece by piece. There's a stem layer right at the start, and then it's followed by a sequence of our inception blocks. Everything flows toward those final layers that make the actual call. Each part is a distinct module, kind of like building with these high-tech, super smart Lego bricks.
Okay, so after all that training, we get to the moment of truth. The model's real test is seeing how it does on data it has never ever seen before. This is called generalization, and it's the real measure. Did the model actually learn what a t-shirt looks like, or did it just memorize the pictures we showed it?
So, what was the result? A test accuracy of over 92%. That right there is the payoff for all that clever architectural design. It's the hard number that proves this adapted GoogLeNet architecture really works. It's getting the answer right on new images almost all the time.
So, okay, getting a good score on a dataset is great and all, but what was the real impact of GoogLeNet? Let's zoom out and take a look at the legacy this incredible architecture left behind. The takeaways from this are they're huge. First, GoogLeNet showed the world how to see at multiple scales all at once.
But maybe more importantly, it proved that you could build a really deep network that was also incredibly efficient. It basically showed that deep didn't have to mean slow and expensive. It achieved championship-level accuracy using just a fraction of the computing power of its rival.
Look, if you take away just one single thing from all this, let it be this. The true genius of the Inception module was that it gave the network a choice. Instead of a human designer having to guess the best filter size, the network was empowered to learn and decide for itself how important different scales were.
You know, what GoogleNet really taught us is that being smart with your architecture can totally beat just throwing more computers at a problem. It proved we can do more with less. And that leaves us with a really fascinating question for today. What is the next Inception idea that's going to once again redefine what's possible in AI? Thanks for diving into this with me.